What's up, everybody? Whoa. What's up, everybody? Today we're going to be doing some studying. It's a little bit different from what I'm usually used to doing, but finals are coming up. Things are getting hectic, and if there's one thing I want to do in this life, it is to pass general chemistry. So it's not really my strong suit, but studying today I'm sure will help just as much as it does every other day. So today, mostly what we're going to be worrying about is what's going to be on the next test, which will be like electron geometry, intermolecular forces, uh, dipole interaction, stuff like that. I have it all written down. Check it out real quick. All right. We're going to have a lot of gas laws. Those are easy. Like I said, intermolecular forces, liquid solids, easy stuff for that. Gonna do a little bit of Lewis diagrams. I'm pretty good at those, so I don't think that'll really matter. But we also got some shape and geometry. We really wish it would focus, but it's okay. Shape and geometry, gases. We're gonna do limiting reagent gases. Those I don't know if I'm good at. I actually don't even think I've tried doing one yet, so we're gonna have to go over that. And hybridization, all stuff that's pretty easy. It's just a bunch of memorization. But we'll see. We'll see how it goes. I've got a few questions right here that we can do, but that'll only last us a little bit, so we can go do a few other things after that. But yeah, it'll be fun. I also have all the electron geometry. Whoa. What? Add that. Are you good? Anyways, I have all the electron geometry setups here with all their angles and how they go. So basically, steric number 2 through 6, all the way to 4 lone pairs, 0 lone pairs. Easy stuff. Tedious work? It's always tedious. It's always tedious. But yeah, I think we should start with the hard stuff first, because I'm gonna be real. I don't even think I've really worked with limiting reagents like at all. Well, I did for limiting yields back in unit 1, but that's about it. But we can do a few of these. Which one do we want to do, though? Alright. There's going to be a lot of trial and error, because I literally have not done this once. But it's okay. Sulfur dioxide gas reacts with aqueous iodine to produce hydrogen sulfate ions and iodide. 0.425 liters of sulfur dioxide gas at 38 Celsius, 311.2 Kelvin, and a pressure of 842.0 millimeter Hg. I forget what that is. But 1.01 atm atomic pressure were bubbled through and reacted with 55 milliliters of 0.3150 molar mass iodine solution. Water is present in significant excess. What is the theoretical yield in moles of iodine? Ions shown. Here, show your work. Alright. I don't even know where we'd start with this. I'm going to be honest with you. Maybe it's not a good idea to start with stuff I have no clue about. You'll probably work through it. Yeah, I have no clue. We're going to start off with stuff that I know. Let's get some good questions here first. You know what? I know what we can do. This is going to go amazing. Just watch. In all honesty, though, I probably shouldn't start with stuff I have zero clue about. It probably isn't the best way to go about it. All right. Dude, I wish I should have had some like ready beforehand. I didn't even think about this. I'm sure I've got some though. I'm not too worried. There we go. We'll do some electron geometry real quick. So BeCl2. I am going to use a standard periodic table for this. It's rounded to the second sig fig on every single one. So it's the most standard one, but other people use other ones. It gives you different answers. It is how it is. Everything's pretty much determined by significant figures. So depending on what you're going to for that, it'll be different. But BeCl2, let's check Be. It has 2 valence and it is 9.01 on atomic mass. And then chloride has 35.45. Okay. Let me keep that to the side because I'm going to need those electron counts in a second. (9.01) plus 35.45 times 2, which is 79.91. Now, if you're wondering why I'm getting the atomic mass of them all together, when you go to find out its polarity, you're going to want the atomic mass plus the configuration of it, the shape of it, because that'll help you determine whether it's polar or non-polar. Usually you're able to tell pretty easily, but it's not always so simple. So Be is a +2 charge, and then Cl2 is a -1 for both, which will be times 2 since there's 2 of them. So Be is definitely going to be the central atom here, with 2 next to it, which would be Cl. Now, both those Cls have 7 each. They have 1 going towards there, so they're going to have 6 and 6. And I think B is just 2. So B is giving all of its electrons already, has all of its bonds. So this is the Lewis diagram of it. Pretty simple. But now we want to get the basic geometry of it. Real quick, I'm going to write down just electron geometry. What all do we want to write down for this? Electron geometry, molecular geometry, polar or non-pole. We're going to want the hybridization. I feel like I'm forgetting something. What am I forgetting? We can include the delta and sigmas too, because those never hurt. Angle. That is what I'm forgetting. And then the angle. That is in the weirdest order ever, but it is fine. It'll do. All right. So since B is giving all of its bonds, as we can see right here, the steric number is 2, so it's going to be linear for its electron geometry. And then for its molecular geometry, it has no single bonds or lone pairs, so it's just going to be linear again with a 180 degree. for it to angle. Now if we're going to finding if it's polar or non-polar, there's two ways you can do this. One by the amount of its atomic mass, and by the just in general of the shape of the atom. So real quick, let's draw, I mean, it's already pretty much there, but we can write the 180 right here. But if we were to slice this in half, it has both sides, so it would be polar. Hybridization. We probably, honestly, do this pretty easily. So hybridization, how that would go, and I'll write it up here. SP for 1 group, 2 group, 3 group. I'll just write it down to 5 groups because I don't think we'll get any there past that. But then it would be S, and then SP1, SP2, SP3, and then SP3D. And then for 6, it would be SP3D2. I think that's right. I always get mixed up on the D's, but it never really gets to that point anyway. So since we're at SP1, I believe. Yeah, because we have 2 groups, so SP1. So that would be the hybridization. And then for the delta plus sig, it will be, I haven't looked at delta plus sig in a minute. Hold up. We can take a check. This is a studying stream, so I'm going to have to go back a million times anyway, so I'm no professional at it. That's why we got music. That's why we're just chilling. It's always nice. I have a lot of questions we can do in here too as well. How far is it? There it is. Okay, so for a singular bond, I'm going to write this down real quick. It is 1 bond equals 1 sigma, and then double bond equals 1 sig, and then 1 delta. These are represented by their own little marks. Actually, I think it's called pi. I don't know why I call it delta, but 1 pi. And then 3 bonds is 1 sig, and then 2 pi. So, looking at it here, has two pairs right here and here. So that means it would have 2 sigs. So it is 2 sigma. 2 sigma bonds. I'm locking in. 2 sigma bonds. All right. So that's the first one we did. That was honestly pretty easy. We kind of rolled through that. I feel like electron geometry isn't that hard. What I really want to achieve today is just getting over the crutch of using this and just trying to memorize it to the best that I can. Because on a test, you're not going to have this. And as easy as that last one was, when we get down to like these down here, it's just so much to remember. So it'll probably be best just to keep doing them and then getting them over time. Here, let me get some more first. There we go. All right, we can do, let me get them just ready. 2 could be NH3. That one will be easy. Or, yeah, NH3. That'll be easy. And then let's get a harder one. The last one here. CF4. Let's do that. And then for 3, CF4. So for NH3, nitrogen is easily going to be our central atom. I always like to draw the Lewis structure first before I try to go into any detailed or advanced electron geometry, merely because getting that those angles and just trying to mess around with that immediately kind of overcomplicates it for me. So I like to just kind of go to the advanced stuff after I've already kind of perfected everything else. So real quick, there. But anyways, nitrogen is going to be our central atom here with 1H, 2H, and 3H onto them. Hydrogen is a single bond atom. And in all honesty, hydrogen loves to just connect to everything. Carbon and hydrogen, CH4, literally loves to connect to anything. So nitrogen, I believe, has 3 or 4. I was way off. It has 5. It has 5 electrons. So 2, 4, 6. We have bonds here, and then bonds here. And these are being shared to the hydrogen. So we would have 2 bonds left. So we would have a lone pair up here. My eraser is going bad. Holy. So we would have a hydrogen, and a hydrogen, and then a single pair right there. So let me write down real quick on the side. We want the EG, the MG. I'm going to write the angle up here because that'll just make it easier for us to remember. We want the polar or nonpolar, and then the hybridization, and then the delta sig, and then that's it. Seems like a lot. It's not in actuality. Most of it you get from the same thing. So if it is going to be 3 normal steric bonds, that means it's going to be a... Gosh, this is going to be me trying to memorize these things over and over today, but I have such a crutch on them. Trigonal planar. I should know that. I really should. So trigonal planar would be its electron geometry. I might be mixing up electron and molecular geometry, but I think it's okay. It's okay for now. Trigonal planar, and then since it has 1, it would be a trigonal pyramid. Since it has 1 lone pair right here. So trigonal pyramid. Now I'm going to go off my head here and try to make the actual angled version of this. I doubt I'll be able to do a good job, but we will see. So it would have 1 up front here. Now, if anybody's wondering what this little triangle is, when you have a filled in triangle like that on a Lewis, it's a Lewis diagram that's a molecularly correct Lewis diagram. That means it's to the front, and then if you have one back here that's kind of scribbled in like that, that means it's to the back. So we have 1 hydrogen back here, 1 hydrogen to the front, and then let's put our nitrogen right here. We would have 1 nitrogen. Hold on. You know what? I'm completely wrong. I'm right on the molecular geometry. Why did I put trigonal planar? This should be tetrahedral right here. I was wondering why it felt so weird. This is tetrahedral for the electron geometry. So HH, and then we would have 1 to the top here. That's going to be our lone pair. And then 1 to the side here. That's going to be our last H. And then the angle between that would be just under 109. So say less than 109 degrees. And then we'll put that there for our angle. Now, is it polar or non-polar? This we can grab here. We can see if it's got conflicting electrons. Nitrogen has a -3 charge, while hydrogen has +1. Is got 3 hydrogens to it. So, and then it cuts through. So that I would say that's polar. I'll fact check that afterwards. So I feel like polars and non-polars I do pretty poorly on. I'm not gonna lie. Only because there's exceptions to the rules, and then I always get those exceptions wrong. It is what it is. So for hybridization, we have 1, 2, 3, 4. So that means we'd have S, sp1, sp2, and then sp3. And then if it's for sig and delta, we have just lone bonds across the board. I don't believe we would count these. So it would just be 1, 2, 3. We'd have 3, so that means 3 sigma bonds. Easy. That's that. And then let's get our last one done here. I'm hoping you guys can see it pretty well. I feel like it's really blurry, but it is what it is. We will. You know what? I could probably do something about that. Let me see if I can find a pen that's a little darker. Let's see here. You can also use highlighters. I feel like that would work pretty well too. Stay over there, buddy. Stay over there. Stay over there. Stay over there. Alright. Okay. Let me check to see if this is a little bit darker. I feel like that's kind of the same level of intensity. Am I wrong? I feel like it is. I feel like it is. Now let me see if highlighting things makes it easier to see here. And then bipyramid, polar. There we go. I mean, slightly. I think it'll be okay for now. Let's just get going on CF4. So carbon loves being that single atom at the front, so carbon will always be right around here with 4 fluorines connected to it. I don't know why I'm using the non-erasable pen. But the fluorine has a negative electron charge. And there's 4 of them. Carbon has a +4, -4. So in this case, carbon would be giving a +4 charge, with each of these fluorine giving a -1. This is going to be most likely a polar atom. I don't think there's any octet rule or anything against that. So fluorine has 7 electrons, while carbon only has 4. So each of these would have 6 lone pairs. There we go. Not the prettiest looking lone pairs, but they will do. They will do. So let's write down our EG, our MG, our angle, polar or non-polar, our hybridization, and then our sig or delta. So immediately, just off of first glance, we could probably get the sigma, and the hybridization pretty easily without diving too much deep into advanced electronic geometry. Okay. But for our sigma bonds, we have 1, 2, 3, 4. So we have 4 sigma bonds. Now, if any of those were a double bond or a triple bond even, but in chemistry, we really don't like to use triple bonds. We try to avoid them with any case that we can. we will have 4 sigma bonds all around. For our hybridization, again, 1, 2, 3, 4, S, sp1, sp2, and sp3. So it'll be sp3, just like our last one was. Now, whether to say if it's polar or nonpolar, that we really can't get into until we get the electron geometry. But I'm going to go on a limb here and say it's polar. One, because if you were to cut it in half, it is symmetrical on both sides, as well as the fact that it has no plus or negative to it. Each thing cancels each other out. The fluorines cancel each other out, and the carbon cancels each other out. There's 4 fluorines, which are equal out to -4, and then there's 1 carbon that equals out to a +4. They go together, nothing equals 0. So I'm going to go on a limb here and say it's polar. Now for the electron geometry, this is going to be tetrahedral. So we'll put tetrahedral here for now. Now I'm going to go on a limb here. I'm going to attempt to get the angles right on this one. I think I can, solely because I don't think tetrahedral is all that hard to do. It's just like before. You have the one out front, the one out in the back. So let's write our fluorine, like carbon right there. And then you have the one here, fluorine, and then you have the one at the top. So our molecular geometry should stay tetrahedral since we have no lone pairs. And then as of the angle, it should be 109 degrees on the dot. All right. It's pretty easy. I'm not going to lie. That was pretty easy. I'm going to get together a few gas problems. I'm going to go through those next. There we go. I'll write them down too, because why not? I feel like that'll make it easier. All right. So for our first problem here, lower this down so it's readable. A reaction between a liquid liquid reactants takes place at (25 degrees Celsius). In a sealed, evacuated container. With a measured volume of 50 liters. Measurements showed that the reaction produced 14 grams of carbon monoxide. Gas. Now we must calculate the pressure of carbon monoxide gas in the reaction vessel. All right. So a reaction between the liquid reactants takes place at 25 degrees Celsius in a sealed evacuated vessel with a measured volume of 50 liters. Measurements show that the reaction produced 14 grams of carbon monoxide gas. We have to calculate the pressure of the carbon monoxide gas in the reaction vessel after the reaction. So as always, when it comes to calculating gas, pressure, or temperature, anything of those sorts when you're calculating with gas or pressure, we're going to use the good old Purvner. At least that's what we call it. Pressure times volume equals moles times constant times T. PV equals nRT. If you've ever taken a chemistry class, you've probably heard that at least once. Now, you're able to rearrange this formula like an algebraic equation to help you find out what you need to find out. So for us, we have to calculate the pressure. So this will be pressure equals, I think it's volume over nRT. I'm going to check that to make sure I'm right, but that should be it. Actually, I got it backwards. nRT over V. So first we want to find the moles. Reaction between the liquid reactants takes place at 25 degrees Celsius in a sealed evacuated vessel with a measured volume of 50 liters. Measurements show that the reaction produced 14 grams of carbon monoxide gas. Carbon monoxide is going to be, what is that, CO2? No, that's dioxide. Carbon monoxide is just CO. Okay. So how we can always find n is finding the mass of the amount times the molar mass, and that will give us the moles per. CO2, I want to say it's like 28.01, but I don't think that's right. C is 12. Actually, it might be right. I feel like I've done this so many times. And then plus 16. So 1, 0, 8, and then 28.01. What do you know? What are you fighting in Dark Souls? I must know. So 28.01 is going to be our moles. And you always want to put something here so you remember it's your moles. So I like put the unit for moles right there. Making sure you have the correct units when doing any pressure, volume, or anything like that is super, super important. Always remember that. So we have 28.01, and then we want to times that by our constant. Now the constant for gas, I believe, is 0.08206 ATM. ATM stands for atomic pressure. When you're doing pressure versus volume, you always want to make sure that you have ATM, or if you're going to use the torr constant, which is like 8 point something, make sure you have torr. Always make sure that those follow those rules. Because if you have the wrong units, they're going to give your calculations all messed up. And then the temperature was 25 degrees Celsius. Now you would think that that is good alone, but no. When you're doing a gas problem, you want to make sure that you convert Celsius to Kelvin, which will be 273.15. So we're going to add 273.15 to our 25 degrees Celsius. So 15, and then it'll be 8, 9, 298.15 Kelvin. 98.15 Kelvin. Oh, I'm running out of page. And then we're going to divide that all by our volume, which was 50 liters, which is exactly what we want. All right. Now we just got to do that all in the calc. There we go. So 28.01. Let's put that in brackets. 28.01 times 0.08206 times 298.15 Kelvin. And then we want to divide that by 50 liters. So that gives us, for our pressure, 13.7. And then we're going to want to use our sig figs here. 28.01 seems to be our lowest. So we're going to do that. 13.71 ATM. And that's our pressure. That one's not too bad, I feel. I feel like as long as you know the basic laws, which are gas laws, we have Boyle's, Gay-Lussac's, Charles, Dusac's law, all the other ones. Here, I've got them all actually written down over here. We can go over them real quick. All right. So for all of our gas laws, we have, there we go. We have Boyle's law, Charles' law, Gay-Lussac's law, and Avogadro's law. And then we have our ideal gas law, which is just pretty easy to remember Pertner. We have Dalton's law, and those are the big ones that you really have to worry about when doing these. gas equations. So always keep that in mind. But other than that, that's it. That's all we had to do for that. So let's dive into these limiting reagents. The only way we're gonna actually be able to do them is just by kind of pushing ourselves to do them and getting the answer. So I'm gonna look up real quick what steps we should go by. Okay. So I'm going to put them right off to here this side. First thing we want to do is balance the equation. Convert all given amounts to moles. And then we have to identify the limiting reagent. So first thing we want to do is balance the equation. It doesn't look like it's already balanced, so easiest way to do this is go off of how many are each column. I am not going to lie to y'all. It has been a quick minute since I've balanced an equation. I feel like ever since I've kind of leaped into general chemistry, going into thermodynamics, never needed to balance an equation. So it'll be a good refresher for me. CO3. I always make my parentheses really they look like C's. I don't know why. And then plus HCl. Which is aqua, but I'm not going to bother with that. Or aqueous. I would call it aqua. It's so much easier for me to remember. So, first thing we want to do is we want to get all of the elements that we have. I like to make a little table. So I like to put the elements here, and then the first, the reactive, and then the product. So we go by here. We can first start off finding each element in here. We have the C, we have oxygen, we have hydrogen, and then we have Fe and Cl. It seems like a lot, but honestly, it's not that much. I'm going to take this up just a little bit, just so we have enough space. Let's go up to like here. 1, 2. So we have carbon, oxygen, hydrogen, beryllium, and then chlorine. And then we have 1 carbon, we have 2 oxygen, 3 oxygen, we have 2 hydrogen, 2 hydrogen, and then 1 Fe and 1 Cl. And then for the second table, we have 2 Fe, 2 Fe, we have 3 CO3, so we have 9 CO3s. So that means we're going to have 3 C's. Put that in action. We're going to have 3 C's and then 9 oxygens. Quite a bit there. And then we have 1 hydrogen and then 1 It's going to be a pain in the butt to balance, but we will get through it, I promise. So first thing we want to do is we want to go up and just see what we can do to kind of balance this equation. First thing with the carbons is we're going to have 1 here. So if we were to add a 3 to this carbon, and we made this 3, we would make this carbon 3, which balances with our carbon over here. This would also make our oxygen over here 6, which honestly kind of helps us. So let's have a 3 there. That makes our carbon 3 and our oxygen 3, so carbon's balanced. And we still have the H2 over here that we can, honestly, we could add a 2 onto, but that would make it 8. So that doesn't help us much. So let's move on to the other side. Let's see. HCl, if we added a 2 to that, we added a 2 to the HCl, that would give us 2 hydrogen. And then 2 chlorine. So that balances the hydrogen out. And then if we were to add a 2 to the beryllium and the carbon trioxide, that would give us 4 Fe2s. Oh wait, why would I add it to that? I'm not adding it to that. We're adding it to this one. That gives us 2 Fe2s and 2 Cl2s. Problem is our oxygens still aren't balanced, so we need to figure out what we can do to balance those. Problem is we need 3 more oxygens going towards here. So if we were to add a 3 to this H2O, we're going to get the 9 oxygens that we need. We are also going to get 6 hydrogens going towards this. So that would make this 6 instead. So then our HCl would have to be adjusted to accumulate for 6. So we would have 6 HCl, which gives us 6 hydrogen. And 6 chlorine. And then we would have to change FeCl over here, which is currently 2. It's going to be a lot of back and forth when you're balancing equations. So HCl, and then we want to get this Cl up, so we're going to have to change this to 6 FeCl, which makes our Cl over here correct at 6. But then it makes our Fe too high, and now it's 6. So now we're going to have to go touch the Fe over here. We're going to have to bump it up by 3. Now if we do this, what will happen? If we hit this with a 3 Fe2, we're going to get 6 Fe, and then we're going to get 3 CO32s, basically 3 of each of these. So we're going to have 3 9s, so we're going to be at 18, 27 oxygens. So 27 oxygens. And then we'll be at, hold on, let me check something real quick. Okay. I'm gonna recheck my math here because I feel like this should be right. We have so we have 3 carbons, 6 oxygens, and then we have 9 more. So 9 oxygens, and we have 6 hydrogens, and then 2 beryllium, and then 2 chlorine. Then on this side, we have 2 Fe's, and then we have 3 carbons, 9 oxygens, so all that's right, and then 6 HCl, so we're going to have 6H, and then 6 HCl. Oh yeah, we have 6 hydrogen. Something's off with this equation. Three CO2, 3 H2O. Oh, there's my problem. I didn't write Cl3 on there. Okay, that changes practically everything with Cl. So we are going to have 6 Cl and then 6 Cl. I knew something was really off with that equation. I could not for the life of me figure out what it was. There we go. So that's the balanced equation for it. So I'm going to write it up here. 3 CO2 plus 3 H2O plus 2 FeCl3. Convert it to Fe2 CO3 to C3 and then 6 HCl. Alright, now we can erase all this down here. Alrighty. That went a little bit better than I expected for not having done a balancing equation in a little while. I was really confused there why it wasn't balanced, but forgetting that 3 really does make a difference. So I guess that's a fair warning to always check your equation, make sure you have everything written down correctly. So we can cross out balance here. That's done. Then we want to convert all units to moles. So solid iron carbonate can be prepared by bubbling carbon dioxide gas through an iron 3 chloride aqueous solution. 3.50 liters of carbon dioxide gas at 68 Celsius. Okay. So we're going to want to use the ideal gas law for this. So to find the moles, we're going to use N equals PV over RT. So our pressure is 722.0 millimeter Hg. What's the conversion for that? What's the conversion for that? Okay, so it's 760 millimeters of mercury is equal to 1 ATM. Keep that in mind. All right. So let's divide the millimeters of mercury, which is 722, by 760. Which equals out to 0.95. So for our pressure, it'll be 0.95 ATM. And then times that by our volume, which is 3.50 liters. He did us the favor of giving us that one. Okay, and then put this over. Our constant will still be 0.08206, which technically is ATM times Kelvin over moles over grams, but I never care to write all that. I usually just write ATM. I know it's the constant pressure. 0.8206 is pretty specific. And then we have a 68 degrees Celsius. So 68 degrees plus so it's 100 or 273.15. So 5, 1, and then 11, 7, 14, 341.15. Okay. And then we're going to want to put that there. That's going to be Kelvin, by the way. 341.15 Kelvin. And then so then we're going to want to put that all into our calculator here. So bracket that 0.95 ATM times 3.50 liters over 0.08206 times that by 341.15 Kelvin. And then we'll get 0.11877 using our lowest one here, which is 2 sig figs. We will go to 0.12. So our moles of, where's that, carbon dioxide gas? Yep. 0.12 moles of CO2. And that is the first of the 2 equations we've got to do. I'm going to write these formulas over to the side here. Because now we've got to do the chloride 3 solution. All right. So again, we'll use N equals per PV over RT. So we'll use the same pressure and volume, which is 0.95. Or no, we won't. We will use a different volume. Oh. Over constant, over temperature, over volume. So we need the pressure. Okay. So for this one, we're going to do P equals nRT over volume. Okay. So our moles would be 0.600. Times our constant, which is 0.8206, or 0.08206. Times times our temperature, which is 341.15 Kelvin. Okay. And then for our volume, which was 250 milliliters, we want to get that to liters, so we're going to times it by 1,000 for our conversion rate. Or divided by 1,000. What am I talking about? Timesing. Which will equal out to 0.25 liters. So then we have our 0.25 liters down here. And now we're going to send it all through to get the pressure. So then we get 67.19. Actually, we did, yeah, 67. ATM. So real quick, you can tell between our 0.12 mole of CO2 and then our 0.600 molar mass of iron. Oh, actually, we got thrown for a curveball there, y'all. Let's redo our calculations real quick. That's molar mass, not moles. I always get them mixed up because they all have the same exact unit. So if we have molar mass, we need to calculate for moles. We need N equals mass times molar mass. We know our mass is 250 milliliters, but that's not what we want. We need milliliters to grams. Okay, we can just put it to 1. So N equals 250 times our molar mass of 0.600 which equals out to 150. It would be 0.150. So let's redo that calculation real quick. 0.150 times, hold on, let's go back right. 0.150 times 0.08206 times 341 Kelvin, or 341.15 Kelvin, and then divide that by 0.25, which equals out to 16.7 atomic pressure, 16.79 atomic pressure. And we can tell between the 0.150 mole of iron and then the 0.120 mole of CO2, we can tell that the CO2 is the limiting reagent. So the limiting reagent will be CO2. All right. Okay. So our limiting reactant being 0.120, we have to multiply that by our stoichiometric ratio, which is going to be moles product over moles limiting reactant. So first we want to put the moles of the product being Fe2, see how the H3O. So we're going to put 0.20 over 0.150. That gives us 0.8. Then we want times that by 1.20. Which equals out to 0.096. And then all we have to do from there is this is the moles of the product. So then we have to go from there and then multiply it by the molar mass. So we'll find the molar mass of the product, which is Fe2. This will be a whole venture in and of itself. For the molar mass, so let's write down 2 FeCl3 All right. Fe2, CO3, 3 plus 6HCl. So Fe iron is going to be, how many molar mass am I? 55.85. And then our C and O carbon's going to be 12.01. And our oxygen's going to be like 16 on the dot. Okay. We're going to plus that by hydrogen, which is 1.01. So 6 times 1.01. And then chloride, which is 35.45. So times that by, so plus 35.45 times actually this is a lot easier because I did not realize that right here it gives us the conversion. So we're just going to do 291.7. Alright, just cross all that out. So 0.096 times 291.7 is 28.0332. So our theoretical yield is 28 grams. There we go. Took us a minute, but we got there. We got there. All right. I think that's enough of doing that right now, because those get me all on edge, I can tell you what. We did a little bit of hybridization, did a little bit of gas linear reagents, shape of geometry, Lewis diagrams, we did all that. Guess we could do intermolecular forces. Here, I have a question here that we could do real quick. I left it unanswered. Let me see if red looks nice on my camera. You guys see that very well? Can't really tell. I feel like that's kind of hard to see. I wish I had a real thick pen that you guys could see through. I don't think I have anything like that. That isn't just a Sharpie. Sorry, apologies for it. You could probably go get an Expo marker, but I don't think that would be appropriate. So I guess for now, black will do. I know black is somewhat seeable. It is not the deepest, but it works. So the pressure in a 10-liter container is 1.20 atoms held at 300 Kelvin, and we have to find the moles. So we're going to want to find the moles, which is N equals M times molar mass. So mass times molar mass. First thing we want to probably do is find molar mass. Actually, I think it's giving us the easiest version of this. So it would literally, I don't even think we'd have to use mass times molar mass. So we can just do N equals, what would it be? It would be like RT over NRT? PV over RT. PV over RT. PV over RT. And then, so we know our pressure is 10 liters. That's exactly how we want it to be. And we're timing that by our volume. Or, it's not 10 liters. That's not our pressure. Our pressure is 1.20 atm. And then times that by 10 liters. Okay. And then our constant will be 0.08206. And then we want to times that by our temperature, which is already put in Kelvin for us, which is 300 Kelvin. So then we want to just do everything in our calculator real quick. 1.20 atoms. Not atoms, it's ATM, atomic pressure. So then we want to times that by 10 liters. And then divide those by 0.08206 times that by 300 Kelvin. And then our moles will be, our lowest sig fig is 10 to 0.49 mole of, doesn't tell us exactly what it is, but 0.49 mole would be our answer. Those ones are pretty simple as long as you follow the formulas. Everything kind of circles back to PV equals nRT, so pretty simple, pretty easy to figure out. Let me see if I have any more of those like that. You know, it's a good thing when you're looking through questions you write down and they're mostly answered. It means you study well when you come back to things, which is always good. It's always good to study hard and come back to things when you need to. All right, here's something that I do want to go over a little bit, is intermolecular forces. Now, it might be a little hard for y'all to see what's on the screen there. Let me see if, no, I don't think that does it any help. But the intermolecular forces here. So, intramolecular is within the molecules. So that's like covalent, ionic, metallic. And then intermolecular is between molecules. So dispersion, dipole, and hydrogen bonding. All of those. I guess the easy way to remember this is covalent, ionic, and metallic, they're all going on in between, or not in between, but like within certain molecules, while intermolecular is happening between molecules. So say C and let's say like a nitrogen and a hydrogen is hydrogen bonding because those two are different molecules that are coming together through a certain bonding process. So strongest to weakest, intramolecular, ionic would be the strongest, while metallic would be the weakest, and then intermolecular, hydrogen bonding would be the strongest, while London dispersion forces are the weakest. I feel like those are pretty easy to remember as long as you remember those specific layouts, which I think is low-key kind of hard to remember because it's just a lot. It's a lot to memorize, so definitely saving that for later. Okay. I can give us a few questions we can do real quick. Okay. So let's get those equations that we had out. So first one is a gas has 250 liters at 1.30 atm. What is V for volume? At 3.80 atm. So that's actually a really good one to go with because that's going to be like something we haven't done yet. So for this specifically, we're going to be using a certain way of going about it called, I want to say it's not Dalton's law. What law is it? Can't remember. Let's see if I can find it here in my notes. We're going to use we're going to use Charles' law, which is V and T, volume and temperature. So we're going to use V1 over T1 equal to V2 over T2. Okay. So a gas has 250 liters at 1.30 atm. Or, no, we aren't using this. What am I talking about? We're going to use Boyle's law, which is pressure 1, V1, P2, V2. Okay. So our first pressure is 1.30 atm. ATM. And times that by 250 liters for our volume. So this will equal out to our first one. So 1.30 atm times 250 liters, 325. I'm not going to bother putting a unit on that because we only need that for the solution for the next one. So we already have one at P2, so that would be 3.80 atm. So 3.80 ATM, divide that over 325, and that will equal out our volume that we do not have. Actually, I believe it would be 325 over 3.80. So our volume 2 would be 85.5. So then our P1 would be, here we can write up the whole thing real quick. 1.30 ATM times 250 liters is equal to 3.80 ATM times 85.5 liters. And boom, this is our missing volume 2. Pretty standard. Everything in gas you can just kind of plug and chug and follow whatever you are missing. So not too bad to figure out there. Next up, let's see what the next one I have is. For 2. A gas has a volume of 3.89 liters. Point 89 liters at 175 degrees Celsius. What is the volume at 25 degrees? Celsius. For this one, we're going to use Charles' law, which is, keep turning off the phone. V1 over T1 is equal to V2 over T2. Oh, wait. Okay. So for our first volume, it'll be 3.89 liters. And then for our first temperature, it'll be 175 degrees Celsius. Now, you could convert it to Kelvin, but since the final temperature is also in Celsius, there's really not a point because you're going to get the same answer either way. So we do that. We take our second digit here, 25 Celsius. Now, all we're needing to find is that volume 2. So using practically the same methods of last time, we solve the equation, the first equation. 3.89 divided by 175 degrees Celsius. We get 0.022. So we know that 25 degrees divided by something is equal to 0.022. So that's repeating 0.022285714. I'm not going to bother. We're going to keep it to 3 sig figs, so 0.022 will work for the time being. So now we just want to rearrange that. So I believe that would be, 25 times 0.022? Or no, I feel like that would be flipped. 0.022 times 25. I don't think it matters, but times 25. Let's equal that out. 0.22 times 25 gives us 0.55. And that'll be our missing volume right there. So 0.55 liters. Easy enough. This is a lot easier than the limiting reagent problems we were doing earlier. So kind of glad we took the easy break for now. So that should be it for question 2. So let me get question 3 up and going here. A lot faster doing those ones. So as long as you know the different laws, you will be perfectly fine on those. Does anyone else hate when they have like auto rotate on their phone and then you don't know that it's on and you go to turn your phone? It's annoying. It's the worst thing ever. All right. For our third question, gas has a pressure of 1.20 atm. 20 atm at 25 degrees Celsius. At 25 degrees Celsius. What is pressure at 100 degrees Celsius? Pressure at 100 degrees Celsius. So, I can't remember what law this is on the top of my head, but I want to say it's Dalton's. I'm going to check before I say anything, because I'm going to curse myself. No, it's not Dalton's. It's pressure and temperature. So this one would be Gay-Lussac's law, which would be PMT. So same verse, same as the first as last time. I'm going to be calculating pressure 1, temperature 1. And then equal to pressure 2, temperature 2. So we have 1.20 atm for our first pressure at 25 degrees Celsius for our first temperature. And then we need to find what the pressure is at 100 degrees Celsius. So right here we have 100 degrees Celsius. Easy enough. And then we want to find the missing variable here, which would be pressure 2. So same verse, same as the first. We're going to do 1.20 atm times 25, or divided by 25 degrees Celsius. We'll find what that equals out to. So 1.20 divided by 25 degrees Celsius, which equals out to 0.048. So now we know that something divided by 100 degrees Celsius is equal to 0.048. So now we just got to reverse the equation here to 0.048 times 100 degrees Celsius. 0.048 times 100 degrees Celsius, which is 4.8, and it'll be atm since it's our pressure. And then that's our missing pressure at 4.8 atm. Easy enough. All right. I'm going to hit you guys with a little bit of be right back, and then we're going to do a few more, and then probably quit the stream early at like maybe around 2-3 hours-ish. So yeah, I'll be right back, y'all. I'll get some more questions ready, and we can get rolling with them. See you guys there in a sec. All right, y'all, I'm back. We got a few more written up here. We'll see where we get with this, and then if we decide to move anywhere else, we can. But for now, a gas has 2 liters with 0.50 mole. What volume will it occupy at 1.50 mole? So this is a volume and a mole question. So it's going to be V1 over N1 equal to V2 over N2. And for anybody wondering, that's Avogadro's law, or Avogadro, however you want to say it. Law. So we take our first volume, which is 2 liters, and our first mole, which is 0.50 liters. Go do this, and we find 1.50 liters. Mole. I don't know why I'm putting liters, it's mole. Just got liters on the mind. Now we need to find the ending volume. So same as before, we're going to do 2.0 divided by 0.50. So 2.0 divided by 0.50 is 4. So this will end out to 4. So now we do our second equation. 1.5 times 4 equals out to 1.5 times 4 equals out to 6. So our ending amount will be 6.00 liters. Easy enough, easy enough. Those ones are quite simple as long as you just remember what they are. And then for the next one, we're going to use Pervner, our ideal gas law. We're going to use PV equals nRT. Hopefully that looks familiar because we've done that before. So we need to find volume. And the reason I immediately know it's Pervner is because we not only are getting asked what volume, but we have moles, and we have ATM, and we have Kelvin. That's exactly everything you need to do a Pervner equation. So if we're getting asked for volume, it's going to be nRT over pressure. Over pressure. So we are looking for the volume. So N, our mole, is 2.0. Times that by our constant, which will be 0.08206. And then times that by our temperature, which is 300 Kelvin. Excuse me. And then divide all of that by our pressure of 1.50 ATM. Two point zero zero. Let's put that in brackets. 2.00 times 0.08206 times 300 Kelvin. Parentheses up, and then divide that by 1.50 ATM. So that'll equal out to 32.84 for our volume, which that will be liters. So our volume will be 32.84, which will equal out to about 33. So 32.82. And then what volume does 3.50 moles of gas occupy at standard temperature pressure? Now for this you can do a thing called the STP shortcut. I actually already wrote down the 1 mole of gas conversion, but the STP shortcut is basically, as long as you have 1 mole of gas, you can find what volume does 3.50 mole of gas occupy STP. Since standard temperature pressure means that you're at a standard temperature and pressure, that means it's going to stay the exact same. So if we have 1 mole of gas, which equals out to 22.4 liters, times that by 3.50 mole, it'll equal out to 22.4 times 3.50. It'll equal out to 78.4 liters for our volume. That one is literally just that easy. That's all you have to do. Solely because it's the STP shortcut. You already have the mole of gas. You can move on. Not often you get asked an STP equation, but when you do, it's certainly helpful. Real quick, I'm going to highlight each of these answers. Hopefully those are easier to see. And then I've got one more back here. Boo, did I scare you? Okay. For this one, looking at it, the gas is collected at 750 torr. Total pressure, water vapor is 24 torr. Or is that 24 or 29? Let me check real quick. It's 24. 24 torr, fine pressure of gas. Since we're finding the pressure, this is going to be Dalton's law. Since I don't see anything else, Dalton's law is P1 plus P2 equals P total. Pretty simple. Usually it's flipped around, but that's the same thing. So our first one, gas is collected at 750 torr. So our P total will be 24 torr. And we got the collected, which will be 750 torr. Let me give myself more space so I can write that unit down. The Lord knows if you don't write the unit down, you'll get smited. So 750 torr. And then plus our P1, which we do not know yet. So basically all you want to do, algebraic equation, flip it around, reverse it a little. 750 minus 24 equals our P1. So 750 minus 24 is 726 torr. Okay. So then our P1 will be 726 torr. Okay. It's pretty easy. All right. Going to check something real quick. See if I can get some more equations and questions to do here. All right, I've got a few more. Okay, hopefully. Whoa. My screen was bugging for a second, but I think it's all good now. Check to make sure. I'm waiting for stream to catch up. Okay, yeah, it looks good now. All right. So I have a little bit different way of doing this, but it'll help us with electron geometry. So 6. Okay. So it has, I'm going to put for electron groups. Bonding groups. And then lone pairs. Okay. So it has 2 electron groups, 2 bonding groups, and 2 lone pairs. And now we just have to find what that electron geometry would be. So we immediately know that it's going to be linear. And then it has no lone pairs, so it's going to be linear anyways. Actually, it has no lone pairs. I put 2 there on accident. But it has no lone pairs, so we know that the electron is going to stay the same. And then for linear, our angle is going to be 180 degrees. Simple enough, right? I think so. Here, I'm going to do this on my phone because it likes to glitch out the stream. Okay. Happened to our audio. There it is. That was weird. Like went away for half a second. Cannot for the life of me find where I found this. Here we go. Okay, should all be able to see that pretty well. Let's let it go in there. Okay. So again, I'm gonna write down 8. There's electron groups. There are 3. And then bonding groups. There are 3 with no lone pairs. Easy enough. So for this one, I'm thinking it'll be a trigonal pyramid or trigonal planar, not pyramid. And it'll be both same for the Um, both same for electron and molecular. And it'll be at 120 degrees. Yep, easy enough. All right, here's where it's going to get a little bit complicated. I'm going to take this up here. I'll just write about. So for this one, we have for electron groups, we have 3 for bond groups. We have 2. And then for lone pairs, we have 1. Now I like to kind of have an idea of what it is, especially when we're kind of adding in lone pairs here. So we'll use X as a reference. The X, so we know that it has 3 groups. So its electron geometry will probably be around the same as a trigonal planar. And I apologize, the music keeps cutting out for some odd reason. I have no clue why. I think it may be closing the tab that I had open. Might have fixed it. We'll see. We'll see. But X, and then we have 1 lone pair to that X, and then other X's bonded to it. So as formed for electron geometry, it's going to follow trigonal planar. And then for bond groups, it's going to follow linear. Or for molecular geometry, it's going to follow linear. Or trigonal bipyramidal, whatever it is. There, we can actually take a look before I make any ideas. Or bent or angular. Bent or angular. That's what it is. So bent means it would be quite literally bent. So bent, and this will be at 120 degrees or less than 120. Okay. Here we go. Not too bad. Okay. And then on to 10. For our electron groups. Our bond groups. And then our lone pairs. We have 0 lone pairs, and then we have 4 electron groups and 4 bond groups. Now, if we have 4, 1, 2, 3, 4, this one's going to be a steric number. It's not going to be like the last one where we had 2 different for electron geometry and molecular geometry. Since we have 0 lone pairs, it is going to be primarily the same one. So for this one, I believe it's tetrahedral. Off the top of my head. And then tetrahedral for the molecular geometry as well. Tetrahedral, I want to say, has 90 degrees. I don't know. We'll figure it out whether or not it does. 109.5. 109.5. That's my bad. And there we go. And both are tetrahedral, so that is perfectly a-okay. And then next one I have, so question 11 for electron groups. We have 4 for bonding groups. We have 3. And then for lone pair groups, we have 1. So the best way we can imagine this is X in the middle, and then we have 3 bonded, so X, 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 and then we have these stoic lone pairs. So best way we can look at this is it's going to be tetrahedral because it has 4 steric numbers. And then since it's got that lone pair, it's going to be, I want to say bipyramidal, but I know it's like CHA or trigonal pyramid. There we go. And since it's got that lone pair, it's going to be a trigonal pyramid. With a less than 109.5 degree. Okay. And that is correct. A good example of that is NH3. So N always has that, as well as its H's coinciding next to it. This is also a form of hydrogen bonding right here, NH3. Because hydrogen bonding only happens between N, F, and O when a hydrogen is bonded onto it. But anyways, let's go on to the next one here. So for 12, we have for our electron groups, we have 4 for our bond groups. We have 2. And for our lonely pairs, we have 2. So let's write this out so that we can kind of envision it real quick. We have X. It has 2 bonds, but it also has 2 lonely pairs. This would be tetrahedral for molecular or electron geometry, like we've been doing, tetrahedral. But it would be a bent for molecular. And the reason for that is because when you are to kind of put it into perspective, your 2 normal ones are going to be, your 2 bonded atoms are going to be like this, while your lone pairs are going to be off to the side like so. So it would be ultimately a bent molecule. And then bent would have less than 109.5. Let's take a look, see if I'm right here. Yep, perfect. Awesome. All right, time to get into the big boys. So 13 for our electron group. We've got 5 for our bond group. We've also got 5. And then for our lone pairs, we have 0. So since our electron group is 5, it's going to stay the same. Now the hard part is remembering what it is. I, for the life of me, cannot remember. So I'm going to take a look. I should have gone for the S. It is trigonal bipyramid. So when we have 5, it is trigonal bipyramid. The best way to remember this, in my mind, is looking at it. So let's just take a look at it real quick. X, 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 X. So you can remember this is trigonal bipyramid because trigonal, triangle, these are formed like a triangle. And then what are you left with after you form that triangle? 2 bipyramid, which could be made with the other one to form another pyramid. So the molecular and electronical geometry, or the electron geometry, is trigonal bipyramid. Now the hard part is finding out what the angle would be. This one might be 90. It is 120 to 90. So this is the first one that introduces 2, 120, and 90 degrees. Perfect. Perfect. All right. Next one. For 14, for our electron groups, we have 5 for our bonding groups. Okay. Now, the good thing about electronic shapes is you can kind of figure out what their name is based off of how they look. So if you're ever trying to figure out the name of what you're going for, take a look at what it is. That might help you. I'm going to be doing just that here in a second. Figure out this next one. So 5. And then lone pairs are 1. So we have 5 electron groups, one of them being a lone pair. So let's put the lone pair up here. And then we have 4 other electrons. That's the hydrogen. Okay. And then now if we take a look at it, we can kind of see that if this were to be arranged, we would have this up here, X. We'd have that posterior, this anterior, and then up with the electron, because those are always going to fly highest. And then one here. And when you look at this, it may not like clearly appear to you at first, but it's almost shaped like a seesaw. This going down, this can go down, and these two holding it up. So I'm going to take a wild guess here. The electron geometry is going to be trigonal bipyramid, like before. And I'm going to guess that the molecular geometry is a seesaw configuration. And it is. Perfect. And look at that. Guessing can get you places. What did I say? Much like the last one, this one's going to follow suit, but it's going to be less than 120, less than 1. or not 190, less than 90. All right, and then all right. I think that's the last of the electron groups we're going to do for now. We'll take a quick look at them real quick. So we ended out on this one right here, which is the sawhorse or seesaw. The reason why it's one so kind of easily to see is because it's shaped like a seesaw. Next, we would have a T shape, which looks like a T, linear, which is literally just like the linear that we started out with. And then once you get to 6, you get to octahedral, square pyramid, square planar, T shape, and then linear. Pretty simple. It's a lot of memorization, but if you kind of remember and use those audio cues, they're pretty easy to tell. Now, I think that's about all the questions I have. Let's see, how deep are we into the stream here today? Take a look. We're about 2 hours and 30 minutes. That's pretty good. Is there anything we haven't gone over? We went over yield, limiting reagent. No, that's probably a better idea. Let's see what we need to go over and see if there's anything. So we went over hybridization, went over gas limiting reagent, shaping geometry. Lewis diagrams kind of go hand in hand with shaping geometry. As long as you know how to do shaping geometry, you'll have no problem with Lewis diagrams. There's not a lot to them that's all that difficult to understand. As long as you just know what the central atom is, or on the other hand, know what atoms are connecting to what, and you can kind of figure that out. I feel like Lewis diagrams are no problem whatsoever. Now, if you struggle with knowing what electrons connect with what, then maybe work on those, but I feel like those are pretty easy as well. Gas laws, we went over those with Boyle's law, Charles' law, Dalton's law, Gay-Lussac law, literally all of them, even Avogadro's law. Intermolecular forces, we kind of glanced over it. I don't think it'll be that big of a deal, so I'm not too worried. And liquids and solids, we went over that with pressure and temperature, Perkner, and all of that. So yeah, that's about all I've got. I honestly, that was a pretty good study stream. Got a lot done. I think gas limiting reagents is something I'm going to come back to before finals, but other than that, I feel like that was pretty fun. But other than that, this is kind of a different stream setup than what we're used to. Usually we're playing games, but I'm saving that for next stream. We've almost finished Devil May Cry 2. I'm excited for that. We should have finished it last stream, but I kind of chickened out last minute because I wasn't sure how long the last few missions would take. But other than that, I'm thinking this is where I'm going to end it for tonight, and I hope you all have a good rest of your night. If you're watching the VOD, hope you're having a good day, morning, afternoon, whenever you're watching it. Yeah. Other than that, I'll see y'all later. Hope you all have a great rest of your night, whether you're on Twitch or YouTube, and see you. Bye.